default. All right, thanks for coming, everybody. Oh, yeah, glad you be here. Travis, I'm glad you could make it. Yeah, he told me he wasn't going to be here, and then this week he told me he would be here. So in his honor, I decided I would just fix my title slide a little bit. Come on in, everybody. We're friendly up here.
Neighborly.
Neighborly. We're neighborly. All right, so this is Project Ubertooth. 2 years ago at Shmoocon 5, Dominic Spill and I gave a presentation called Building an All-Channel Bluetooth Monitor. And I stood in front of you guys and I said, sniffing Bluetooth is hard. And we went on to describe the progress that we had made with GNU Radio and the USRP. And I think we had some pretty interesting results, but admittedly, the solutions that we presented were somewhat kludgy, and they required a hardware investment of $1,000 or more. And as one of you guys later pointed out to us, at the beginning of our talk, sniffing Bluetooth was hard, and at the end of our talk, sniffing Bluetooth was hard. So I set out to make Bluetooth sniffing easy, and this is the story of that effort. So I'm going to talk about, I'm going to show you Ubertooth 1, which is the latest fruit of my labor, and we'll do a little demo and talk about its capabilities. But mostly today, I'm telling the story of this project, how I got from there to here. And hopefully along the way you'll learn some things that could help you if you want to build your own Ubertooth 1, or if you're inspired to design some entirely new electronic device. So why is Bluetooth sniffing so hard? And maybe a better, more specific question that you might be wondering is, why can't we use an off-the-shelf Bluetooth adapter? Why don't off-the-shelf Bluetooth adapters support monitor mode? We're spoiled, really, I think, by plentiful and affordable Wi-Fi adapters that support monitor mode. Why can't we do the exact same thing with Bluetooth? Well, there are some technical features of Bluetooth that make this difficult, if not impossible. One is that it's a frequency hopping system, and so different Bluetooth networks are transmitting on different channels at different times, and unless you have some kind of prior knowledge of the hopping sequence, you have a very low probability of capturing any one particular packet if you're a naive monitor. Another problem, and this may be a more severe one, is the packet format itself. There's the Bluetooth packet over the air starts with a very short, just 4-bit preamble of alternating ones and zeros. And then the first recognizable part of the packet is an access code that is derived from the LAP, the lower address part of the Bluetooth device address. And so it's device specific. And so you have to program your receiver to look for a particular access code that belongs to a particular device. And when it sees one, it says, aha, I have a packet, and processes it. But if you do that, and another packet comes along from a different Bluetooth device with an address that you didn't program into your receiver doesn't even recognize that a packet existed at all. And in every case that I'm aware of, this correlator, this pattern matching, is implemented in silicon. And then there's a third kind of challenge, third technical feature of Bluetooth that makes passive monitoring a challenge. And that's that the packets are whitened or scrambled by XORing the data to be transmitted with a pseudo-random sequence. And this is really done for RF and electronic reasons, not so much as a security measure, but it makes it considerably more difficult for a naive monitor to decode arbitrary Bluetooth packets from the air. And so all of these problems, they have solutions. And in my talk with Dominic 2 years ago, we went over a lot of solutions, and now I'm just trying to make them a little bit easier to implement. But my point in all this is that a Bluetooth adapter must be specifically engineered for passive monitoring. At the time of product development, you pretty much have to consider those three things. and build a device that can do passive monitoring. It's a more expensive, more complicated proposition than normal Bluetooth operation. And therefore, it is very unlikely that consumer products will be engineered with this goal in mind, right? So it's been 10 years that Bluetooth has been on the market, and we still don't have an affordable monitor mode device. And I mean, how many of you guys have ever done a Wi-Fi security assessment of any kind? How many of you have ever done a Bluetooth assessment of any kind? Keep your hand up if you think it was any good. Okay, there's one hand. Actually, I'm going to put my hand down, and I think there's one hand left in the room, and it's Josh. Okay, so what do you do if you want to make sure that your Bluetooth devices are implemented in a secure fashion? Well, you can hire Josh Wright, okay, but which I strongly recommend. But wouldn't it be nice if the rest of us could do some of this kind of work too? And Josh, Josh, by the way, is the author of the Bluetooth chapters and some other chapters in Hacking Exposed Wireless 2nd edition. Woohoo! Good book. Everybody should pick up a copy of that book, because really the techniques that I'm using were really best documented in his book. So of course I'm doing my darndest to make it obsolete as soon as possible, but generally speaking, I'm just working on a new hardware platform to do the same techniques that I described with Dominic a couple of years ago, and that Josh has put down on paper in his book. So, but there are we have this situation where we just don't have good tools, and there are 1 billion Bluetooth devices manufactured every year. 1 billion. That, I believe, is more than Wi-Fi devices. And I think that as security professionals, we do ourselves, our employers, our clients, and the general public a great disservice by just ignoring Bluetooth vulnerabilities because we don't have adequate tools. And thank you. And so I'm kind of, I'll mention Josh again, I'm kind of following Wright's Law here. Hey, by the way, is there a Wikipedia page for Wright's Law yet? No? Yeah, somebody get on that, right? Okay, so, I mean, Wright's Law, if I may paraphrase, is that, vulnerabilities will be ignored until tools are accessible. And that is really the motivation of this entire project. I think that this problem is too big to ignore at this point. And so I established a goal 2 years ago, just after Shmoocon. I said, I want to build an open source Bluetooth sniffing platform. And it should be widely available. Anyone should be able to build one of these things. Anyone should be able to acquire one of these things. It should be low cost, and it should be portable, right? Because we're dealing with portable technology. And Josh doesn't want to carry around an extra laptop just to have the PCMCIA slot for this ancient piece of hardware that happens to do this hackish thing that he needs. And it should be, I wanted it to be somewhere in the neighborhood of $100. I figured, back in the golden age of Wi-Fi hacking, like when AirSnort first came out, there were Wi-Fi cards available in the $100 price range that could do monitor mode. And that's when everybody started hacking on Wi-Fi, and we actually accomplished some change, right? I mean, Wi-Fi security used to really suck, and now it's improved a lot, right? Bluetooth hasn't gone through that change because nobody's hacked on it very much. So I wanted it to be somewhere in that kind of $100 price range. And I didn't know much about electronics at the time, but I knew a fair bit about software radio. So I thought, well, maybe I could design some kind of a software radio peripheral that's kind of special purpose. Maybe it only works in the 2.4 gigahertz band. Maybe it can't do much more than receive Bluetooth. But maybe I could build it out of kind of consumer bits and pieces of consumer devices, so it would be really affordable, right? So I thought I'd have some kind of an RF front end with an antenna on it, connected to some kind of an analog to digital converter that stuffs samples into a PC, and then we can use the GR Bluetooth code that we wrote to work with GNU Radio and the USRP with a new hardware platform. So I started looking at options for front ends, and I thought, maybe I can rip some kind of a part or a component out of a cordless phone or a baby monitor, or one of these a video sender, one of these 2.4 gigahertz consumer devices that are on the market. And what I found was that almost without exception, these kinds of products are built around wireless transceiver ICs that are highly integrated. They have their analog and their digital components all on one chip, and you can't really get access to that baseband layer that I was interested in, which is the exact same problem I had looking at Bluetooth chips, chips that are actually made for Bluetooth. So I started to get the idea that maybe I was going to have to kind of roll my own front end somehow. And then I was looking at the back end, the ADC with some kind of a computer interface, and I looked specifically at TV tuner cards and some other things. But TV tuner cards, there were some hackable ones that I could get like in a PCI form factor that I could kind of use as a general purpose ADC. And that looked kind of attractive, but I wanted it to be portable, and a PCI card was kind of a mess. And I never really, there are some USB TV tuner products that are worth further study, but I basically was kind of coming to the conclusion that maybe I was going to have to roll my own back end too. And this was only a little bit terrifying. And many of you, I'm sure, recognize this as Ohm's law, which is really important to know if you are working with electronics. And it really nicely sums up absolutely everything I knew about electronics at the time. I had never designed a digital circuit of any sort. I had never programmed a microcontroller. I had never soldered a surface mount IC. I had never designed a circuit board in my life when I started this project. But hey, I can learn. So I started working on a lot of little electronics projects and microcontroller projects, and I kind of started small, and I was reading a lot of books, and I was talking to a lot of smart people, and I was just trying to learn this stuff and figure out how I would eventually get from point A to point B. And I spent a lot of time reading data sheet after data sheet after data sheet, and frankly, I didn't understand what I was reading. And I don't know that I could have gone about it any differently. I had to read a lot and a lot and a lot and keep learning a lot and a lot and a lot, and gradually they just made more and more sense over time. But these are just absolutely essential documentation for the parts that you might use in an electronic device, and you have to learn how to read them and make sense of them in order to use the parts effectively. But as I was what's that?
Where's your graveyard?
Where's my graveyard? Maybe I should have a photo of my graveyard. But I have quite a graveyard going. But as I was reading these data sheets, I was learning more and more that the component that would probably be the central feature of my Bluetooth sniffer would be some kind of a microcontroller that would probably be reasonably high speed, so I could do some of the things that I want to do. And I noticed that a lot of microcontrollers have integrated ADCs, and that might be handy as long as I could find one that's fast enough to sample Bluetooth, which is 2 megasamples per second, which is pretty high for a low-cost microcontroller. And also some microcontrollers have integrated USB. And I thought, well, wouldn't it be cool if I could find a single microcontroller that had an integrated fast ADC and an integrated high-speed USB. I couldn't use full speed. I had to use high speed to do this software radio approach, because I had to be sending somewhere in the neighborhood of 10 to 16 bits 2 million times per second. I had a hard time finding a microcontroller that kind of met this particular ideal solution, although Atmel came out with a SAM3U that looked like it would at least come close. And so I ordered a SAM3U and then headed off, a dev board, and then headed off to Tour Camp. Yay, Tour Camp! Who's at Tour Camp? Yes! Exactly, yeah. I mean, what's not to love about living in inches thick Mount St. Helens ash? At Tour Camp, I went, and met a lot of great people. And this is what was so great about tour camp for me, was that I met a lot of really interesting people, and people who ended up helping out with this project in one way or another. In particular, I met Mr. Travis Goodspeed at tour camp, and I also met Jared Boone at tour camp, and good times were had. I was, some of you may remember Jared Boone. In particular, he was one of the guys who did the electronic music performance in the Power Dome, which was outstanding, I thought. And he was also the organizer of the Dorkbot PDX camp, which is the group of people that Dominic and I kind of randomly ended up camping with, which was great. And Dorkbot is like a global collective of artists and hackers who do strange things with electricity. And the Portland group, Dorkbot PDX, put together this camp that went to tour camp, and I ended up getting to know those guys, and Jared ended up helping me out with a lot of things down the road. So probably most of you who did go to tour camp like came home on like Sunday. Yeah, Camp Dorkbot was the last camp standing. We stayed till Monday, which was an experience because we spent the entire night hiding out inside a shipping container from terrifying windstorms. With a toy guitar and a dozen friends and a few cases of Rainier beer. So you guys missed out if you left on Sunday. So when I got home from tour camp, I got my SAM3U dev board, yay! And I started playing with it. Oh no, it was terrible. There were some problems, and partly it was just my own, greenness. I didn't know what the hell I was doing, but I managed to get some things working, but with some big caveats. I mean, one caveat was the analog to digital converter. Now, it's advertised as a 1 megasample per second ADC that supports 8 channels. And Jared told me this would be the case, but I had to, be an idiot and prove it for myself. But he said, if it's a 1 megasample per second ADC and it has 8 channels, that means you can only get 1 megasample per second, and any one of those samples can be from any of those 8 channels. Right? But you can't run 2 channels simultaneously, both at 1 megasample per second, which is what I wanted to do like quadrature sampling for a software radio approach. And so that didn't work out. And then another problem is that I didn't even get 1 million samples per second. I got 800 kilosamples per second maximum. And I worked with Atmel support on this issue, and they were very helpful up to the point where they said, oh yeah, you're not going to get any faster than that. They said, oh yeah, the ADC is working at 1 million samples per second just fine. There's just a problem where we can't deliver the samples to the CPU fast enough. Oh, okay. So, I mean, if it said in the documentation, say 1 microsecond conversion time, and there was some extra hidden little delays that I'd have to figure out for myself, that'd be one thing. But if you're going to say that it's 1 million samples per second, it sure would be nice to actually be able to get 1 million samples in 1 second. But I learned a lot from this experience. I mean, in particular here, I learned that if you're reading a data sheet and you look at some kind of maximum value and you want to run at that maximum value, there's a good chance you're going to be in trouble. Another problem with the SAM3U, I ordered my dev board in the summer of 2009 and got it right away. And then following March, I was like, oh, maybe I can order some chips. Oh, 17-week lead time on those. So I checked 17 weeks later, and it was, 26-week lead time. Oh, yeah, and I just looked yesterday, and manufacturing delays have been reported. No kidding. Yeah, this has been like a year and a half, and there's still 0 stock anywhere. So all these experiences kind of pointed me towards this direction that I needed to make some part requirements. And meanwhile, I was looking at what would I plug into the front of my SAM3U or whatever backend I had. And I was looking at some integrated circuits that were coming out for WiMAX and now LTE and some TV tuner chips that looked interesting. But all the ones that looked like most optimal for my application were brand new things that were coming out and were not widely available. And I thought, well, maybe I could convince the manufacturers to send me some documentation or send me some sample chips or something. So I thought maybe I could just pretend that I'm a company that's designing a product, right? So I drew this little logo and I created a website for Great Scott Gadgets, and I put and I started emailing these vendors and calling people on the phone and trying to social engineer my way into, you know, some extra documentation and parts and things, and it didn't work at all. I think the net result of all this effort was like one piece of documentation and 0 chips. So if you were going to pull this off, you would probably have to do a much better job of posing as a bigger company that could actually buy like 100,000 chips. You know, I did have some email conversations that got me maybe a little further along, but it didn't really work. But what if it had worked? What if I'd gotten some chips? What if I'd gotten some documentation? They said, hey, sure, sign this NDA and we'll give you this documentation. What good would that do me for developing an open source product, right? I want anybody to be able to build this. I want anybody to be able to understand this. So it turned out I was going in the completely wrong direction. I should have established from the very beginning my part requirements. My requirements should be that parts are available to everyone, right? They should be available in single quantity so that somebody can just buy enough parts to build one board if they want to, right? And the parts must have public documentation that you shouldn't have to sign an NDA to read, right? I mean, this is like the stuff I should have thought of on day one, and I didn't, and I had to be an idiot and go through all this nonsense before I figured it out. But meanwhile, I was working on a variety of microcontroller projects, most of which I don't even have photos of or anything, but I do have a photo of this one. And hey! So I wrote this spectrum analyzer application for the Girltech IME, which is so cool and so connected. And so cool, so connected. So anyway, I was introduced to the IME last year at Shmoocon by Travis. Thank you, Travis. You know, we were hacking in the hotel bar amid the terrible snowstorm and for hours on end. And Travis got me looking at the chip that's in the IME and the other chips in this ChipCon family from Texas Instruments for this project and for some other projects that he encouraged me to work on. And it was that prompting that made me go back and look at some of these chips that I had actually looked at before and then forgotten about. I went back and I found notes from months before about the CC2400 that when I read its datasheet the first time, I didn't really fully understand what I was reading because I was an idiot. And then when I looked at it again after months and months and learning a lot of stuff, I finally looked at it with kind of a different perspective, and I said, hey, this thing is a transceiver, wireless transceiver. It operates at the 2.4 gigahertz band and it supports a modulation of 1 megabit per sample Gaussian frequency shift keying, which happens to be the exact same modulation that Bluetooth uses. And it has, I think the main reason I ignored it the first time I looked at it was because it had this rigid packet format that you have to use if you use the primary serial interface to talk to this chip the way that it's mainly designed to be used, so that you know, you can only transmit and receive packets that fit this particular format, which is somewhat flexible, but it did not support Bluetooth, right? Completely incompatible with Bluetooth packet format. But there's this thing called unbuffered mode, which is, there are some other chips that have similar thing. It's called direct mode or some other things. It's a secondary serial port on the chip that allows you to kind of open up, tune the radio, turn on the demodulator, and start streaming bits out the secondary serial interface nonstop, and completely bypass the packet handling capabilities on the chip, and do it all yourself, which was perfect for my application. So a couple weeks after Shmoocon, I was stuck in a snowstorm in Boulder near my office. Storms are figure into this story a lot. And I kind of jotted down the Ubertooth architecture for the first time, which is really simple. It's an antenna connected to a CC2400 transceiver connected to a microcontroller with a full-speed USB interface. I didn't have to go high-speed USB interface because I'm not dealing with raw radio samples anymore. I'm dealing with demodulated bits at only 1 megabit per second. And so I can deal with that over full speed. And this is really the basic architecture of Ubertooth today. So Jared Boone, who I mentioned earlier, was also interested in this CC2400, and he was kind enough to design a little breakout board. So he had some built in the Dorkbot PDX PCB order, which is a group order run by a guy named Lane in the Dorkbot PDX group. And you can send him your design files, and he collects a bunch of little designs from a lot of people and panelizes them all together and gets these boards built really affordably. It's only like, I don't know, a few dollars per board, depending on how big your board is. And so Jared had some of these made and sent me a couple, and I got them working. And the first thing I got this working with was a good FET. Thank you, Travis, again. And so I just talked to the CC2400 using the good FET and just made sure that I could tune its radio and stuff like that. And then I got it working with a couple other microcontrollers, and eventually settled on this LPC 1700 microcontroller from NXP, which is an ARM Cortex M3 processor with an integrated full-speed USB interface. And so I got a little development board for the LPC 1700 and connected the little breakout board with it to it and connected the USB interface to my computer. And this was like the first fully working prototype of the Ubertooth architecture that I actually decoded packets with. And so using that, I designed the Ubertooth Zero, which I had some circuit boards made, through Lane service at Dorkbot PDX, and had some boards ready for TourCon, and some of you I know were at my little preview talk I gave there. And so fortunately, I was able to get a few boards working there. Yay! And then I as soon as I got back from TourCon, I immediately set out to work on Ubertooth 1, which is like the finished product in my mind. I mean, it's the Ubertooth 0 was kind of always meant to be a stepping stone, and Ubertooth 1 I started working on, and I originally wanted to I wanted to get like my first working prototype done by, say, the end of November. I got it working on Tuesday. So I really it's been a big learning experience, and I've spent so much more time on the hardware that the software has really suffered a little bit, but that's coming along too. And a lot of the software is really kind of just being adapted from our old GR Bluetooth code for GNU Radio and the USRP. So they're all techniques we've done before, and just applying it to a new package, new platform. But there is a big difference between the CC24. I'm sorry. There's one main difference between the Ubertooth 0 and the Ubertooth 1, one functional difference, and that's the CC2591, which is an additional little amplifier chip. It improves both the transmit power and the receive sensitivity. But I found that the reference design from Texas Instruments was a 4-layer circuit board, and I had never designed a 4-layer circuit board before. I did Ubertooth 0 in Eagle, which is pretty good software, but it's crippleware. I would have had to pay an additional license fee to open up the 4-layer functionality. And I thought, well, it's not that much of a license fee. It's really not that expensive. So I was about to do it, and then I thought, well, should I really have an open source project that people can't modify without licensing some software? I thought that'd be pretty lame. So I decided I should try KiCad. And I am so glad I did. It is, I think, an outstanding piece of software that really met my needs. I was able to design the 4-layer circuit board, and I'm using it for all my projects now, and I highly recommend it. So I designed the Ubertooth 1 in KiCad and had some boards built. Lane at Dorkbot PDX is, in fact, doing 4-layer boards now. He doesn't do the orders as frequently as he does 2-layer orders, but they're still available and very affordable. So this is the Ubertooth 1. It's a little USB dongle that, well, actually, it's kind of big for a USB dongle, but it's quite a bit smaller than the Ubertooth 0 was. And it just has an antenna connector, the CC2591 front end, and a CC2400 wireless transceiver with an LPC 1700 ARM Cortex M3 microcontroller with a full-speed USB interface. Really simple, right? I mean, there are a million products on the market that have something similar to this architecture, right? Like every little dongle that you can find that's a development board or something that comes with a mouse or a keyboard. I mean, they all follow something similar to this, but none of them quite did what I needed them to do for passive Bluetooth monitoring, so I had to roll my own. The chip itself, you can actually use, if you're building one of these, you can use any of these from the LPC 1750 family. They all are pin compatible, and theoretically any of them could work. I recommend going with at least 128K flash. I haven't written any firmware that uses anywhere near that much yet, but I can imagine having firmware that does. So that's probably kind of a good target for the minimum, design minimum. The boards that I'm giving out today have the LPC 1759 in them. So you can, I don't know, maybe even fit like a whole Bluetooth stack in there. I don't know, probably not, but maybe. But I'm not going to do that. I don't know about you. So let me just do a little demo, and this is going to be like the quickest, easiest demo I think I've ever done. I'm going to take my Ubertooth one, and just for good measure, I'll put a slightly larger antenna on it. And yeah, I figured everybody would want to have external antenna capability, so I didn't even bother with the PCB antenna stuff. All right. Let's see. Here we go. So this is a really complicated demo. I plug in the Ubertooth, I type Kismet. Yay, Kismet! And we see if there's any Bluetooth in the room. Hey, look at that! So, so that's really all there is to it. And right now, all I'm doing is just passive monitoring of these lower address parts. You'll see that I'm only filling in the bottom 3 bytes of the device address. But hey, Josh, tell us how many bytes you need before you can start attacking a Bluetooth device. 4? I thought he was going to say 3. No, you need 4, but the 4th one you can get with a really simple brute force attack. Using a script that Josh wrote, or you can use techniques that are in the GR Bluetooth repository that we've done with GNU Radio and the USRP to recover the UAP automatically with passive monitoring. And I don't have that working inside the Kismet plugin yet, but I probably will really soon, like this week, because it's all just stuff we've done before, and I just haven't gotten to it because I've been so focused on the hardware. So recovering the rest, that next byte of the address is something that will happen very soon. It's going to be easy to do. Recovering the upper 2 bytes of the address can be done in some cases as well, but you don't really need it for any of the things that you'd want to do. What you really need to know to do any kind of practical Bluetooth assessment is just the address. You just need a passive way to discover the address, and then you can do everything else with like off-the-shelf dongles. So there's a lot more that we could potentially do with Ubertooth, but the fundamental kind of killer app that we really need is just simply recovering the address, which we can do here, and Kismet lets us automatically log it, and we'll be able to integrate it with GPS and all that stuff that you can do with Kismet down the road. So that's my demo. Yay, surface mount technology! So, when I had first several months of this project, I saw some really impressive surface mount work, surface soldering work being done by people like Travis and Woz and the SparkFun guys, and I said I want to have nothing to do with that. I thought I really didn't want to use surface mount parts at all. And then eventually I kind of came around to the idea that it would be a necessary evil. And then eventually I actually learned to love it, seriously. Surface mount parts are small, they are cheap, and they are fast. And by fast, I don't just mean that they're fast to assemble. I mean that they operate with signals at higher frequencies. They do things that older parts that are bigger, that have leads that are longer, simply cannot do. There are physical limitations. And so surface mount technology is so great because it enables to do fantastic things like build a Bluetooth sniffing dongle. Wouldn't be possible without this stuff. So, and it's really not that hard to work with as long as you kind of follow the advice of people like Woz and do this kind of reflow technique. The first thing you need to do is order PCBs. And you can get them from Lane's Dorkbot group order. You can get 3 of these 4-layer PCBs for $18. What a great deal. Then you need to order a stencil. I highly recommend it. I used to try different ways of applying solder, and oh, yeah, you're laughing at me now. Yeah, right. Yeah, it is painful. And let me tell you, using a stencil is just a dream compared to any other method you could possibly use. You can buy a stainless steel stencil that's good for thousands of uses for, I don't know, a couple $100 or more, but you could also order a Kapton or Mylar stencil. This one's a Kapton one for only like $25. And it's good for dozens of uses at least. Actually, Jared from Dorkbot came up with an interesting method recently. He just stuck some Avery labels into a laser cutter and had them cut. Right? I mean, why spend money on expensive material like Kapton for a stencil that you're going to use on 1 to 3 circuit boards? Right? It's cheaper to get 3 Avery labels than it is to get 1 Kapton stencil. Hey, I have a friend in Colorado who has a laser cutter, I remembered, so I called him up and said, hey, let's try this. And we did, and my result was not as good as Jared's. I had some problems where like the adhesive would stick to the board too much. Right? He found that as long as he got the thing off within a few minutes, that it didn't really stick. But I found that it was more adhesive than his. So this process probably needs to be refined some. There are some other materials I like to try. Like, for example, there's Post-it craft paper. It's like a Post-it note, but it has the adhesive over the whole thing. Having a little bit of adhesive is actually really kind of nice. It makes the stenciling process easier as long as it doesn't stick to your board permanently. Yeah?
I actually recommend if you're going to buy anything with adhesive, use 3M. Because
Right.
when you buy cheap adhesive, it adheres to stuff. But the 3M stuff always comes off really
Right. Okay, so Waz is agreeing that the 3M adhesive is probably a good way to go. But one way or another, I mean, at the worst, you're buying like a $25 stencil, and we're also looking at ways that we can probably reduce this cost. So then you need to get a fine-tip pair of tweezers and place the components, and this isn't as hard as it might look. When there's a little solder on all the pads already, they kind of stick a little bit, and you just kind of go cross-eyed for a while, and everything around you starts to look really big, and then you put the thing on an electric skillet and just heat it up until the solder melts, and you're done. And you should get yourself one of these infrared thermometers. You don't really need one; they're just fun to play with, and it's thanks to these techniques to work with surface mount technology that allowed me to get it small enough to fit inside an enclosure. So you can buy an off-the-shelf enclosure. Personally, I prefer to just put a little transparent heat shrink around it. I find that protects it quite adequately, and it's cheap and easy, and you can still see the blinky LEDs. But if you would rather your Ubertooth look like something you bought at Best Buy than something that some dude lost to you in a poker game at a HackerCon, then maybe you want an enclosure. So what's the total cost here? The bill of materials, all the stuff that's soldered onto the board, is about $40, which is slightly higher than the Ubertooth Zero was.
List of materials.
A list of materials?
Can't say bomb.
I can't say bomb. I'm gonna say bomb if it kills me. And then you can get PCBs using Lane's Dorkbot PDX group order. You can get 3 of these 4-layer PCBs for $18. Does he know that I'm promising that? I think so, actually. Yeah, I told him I'd tell people about it. And his prices are advertised on the Dorkbot page. It's a community effort really that he kind of coordinates, and it's a really nice service. The stencil you can buy for about $25, and maybe we could reduce that even more if we get some of these adhesive things or lower cost, paper kinds of things working. And you'll probably want an antenna, and you might want an enclosure, and all together, we're looking, not counting some extra parts that you'll probably need when you screw things up, not counting some solder and tools, which maybe you have from other projects, and not counting some various shipping fees. This whole thing is under $100 for somebody to build just one, which was my original goal. And what can you do with this? Well, we've seen that you can do basic rate Bluetooth monitoring, which is kind of my original goal. But thanks to the fact that I'm using a transceiver here, we can also do injection. Yay! Bluetooth injection! And I'd love to give you a demonstration, but I haven't written a lick of code. Oh, Josh, you got something working in the last hour, Josh? No? Probably because I haven't given you a board yet. Anyway, we should be able to do basic rate monitoring and injection with this platform, and we've already demonstrated the monitoring. We should be able to do Bluetooth low energy monitoring and injection. This is a new standard that's coming out like right now, and the consumer equipment is going to be on the market any day now, following this new specification. And so we're going to hit the ground running with Bluetooth low energy because we're going to have a platform for it from day one. 802.11 frequency hopping spread spectrum, which some of you know about. You might have seen Rob Havel's work on using USRP for this, and we should be able to sniff and inject that too, do some basic spectrum monitoring, and probably things I haven't even thought of. So overall, I think it kind of fits a niche that we needed, capabilities that needed to be available in that lower cost solution. What, did I pay Gartner for this? Oh yeah, sorry, I should have credited this. You caught me. I plagiarized this slide from Gartner. Yeah, and the original goal for this project was to make this kind of technology, this basic function of Bluetooth sniffing, accessible for everybody, right? And so part of that, first of all, absolutely must be open source. And that's my primary goal, is to make this available open source for everybody. Second of all, I know that there are some people who don't want to solder surface mount components like I love doing now. And so for those folks, I am trying to make some available for sale. So I said, hey, I've got this company. Why not? I'll just, pretend it was legitimate all along. And so I'm actually trying to, produce some of these for people. And I'm doing an initial run, I hope, funded on Kickstarter.com, which is a really neat platform for this kind of thing. It's kind of a crowdfunding thing. It's basically a trusted third party that allows people to place pre-orders from people like me as an independent designer. And so there's a pledge period on Kickstarter.com for 30 days that starts today. So I sincerely hope you all go home and build your own Ubertooth one, and then tell your friends to pledge on Kickstarter. And I want to say thanks to a bunch of people because I learned so much through this 2-year journey, and I really couldn't have gotten to where I did without the help from a lot of people. And I want to call out, in particular, Dominic and Jared. Dominic put so much work into the GR Bluetooth project, and the work that we did together really kind of laid the groundwork for the idea that this kind of solution would be possible at all. And Jared Boone, among all the people who helped out, he really has been my mentor on all things electronic. So thanks, guys. I want to point out before I go some related work. The Killer Bee project of Josh's is really an interesting project that you should all check out. He has kind of a similar solution, but he was able to use an off-the-shelf board, development board that Atmel makes. And so he didn't have to go through all this nonsense of trying to design a board from scratch, but it's a similar kind of architecture with similar kinds of goals. The Kikiriki project, or their first version, was working on keyboards in the 27 megahertz band, but the V2 that they've been showing off in the last year is 2.4 gigahertz proprietary keyboards, and they've had some really interesting results, and they've run across many of the same exact challenges that I have, and it's an open source design that you can download. And the Next Hope badge that Travis Goodspeed designed last summer has some really interesting applications here too. And one of these days, like maybe this week or next, tomorrow, Travis is going to drop a bomb. See, I said it again. And put put some really interesting results, things that he's been able to accomplish with the Next Hope badge on his blog. And these are just some examples of a lot of these open source hardware projects that are going on in our community now. And these are ones that really kind of relate directly to wireless security research. And it really gives me a lot of hope. I'm really excited to be a part of this, and that our community is kind of bridging the gap between software expertise and hardware expertise, and producing the solutions that really can only be done with both. And because in the future, we're not going to wait around for 10 years for somebody to build a device that can do the basic things we needed to do, right? When a new standard comes along, a new popular standard for wireless communication technologies comes along, we're not going to wait around for 10 years. We'll just build it ourselves. So, thank you. What was on that sign? Was it fallopian tubes or what? I don't. Okay. So do we have a couple minutes for questions? Yeah? Are you okay? Any questions? Really? None? Wow. Oh, Travis.
How about a race toward Bluetooth Low Energy?
A race toward Bluetooth Low Energy? What?
Kits arriving about this week.
What's that? Oh, are you challenging me to a race?
I'm challenging you to a race.
Oh, we have a challenge.
Neighborly race.
A neighborly race. Okay. So, Travis, I'm going to try to get Bluetooth Low Energy sniffing working on Ubertooth, and you're going to try to get Bluetooth Low Energy sniffing working on the Next Hope badge?
Good bet.
Or with a good fit. Okay. So the race is on. I accept your challenge. Anyone else? Yes. Oh, can I sell kits? Maybe. Right now, I've just been totally focused on getting boards made. I mean, I have 4 boards to give away this weekend, and that's it. And just got the first one working on Tuesday, and just trying to get this Kickstarter thing rolling, and we'll go with that. But once the Kickstarter thing is kind of plays out, then yeah, I'm going to look at more ways to make boards available to people, and kits. A kit is definitely something. Actually, on the Kickstarter site, at one of the lower pledge levels, I have where you can just get like a PCB and a stencil and a serial programmer, and then do the rest yourself. So that's an option that is available today on the Kickstarter site. I'm just not going through the effort of like parting out all the entire bomb for you. Yes. Oh, have I asked Mudge for a pledge? Not yet. Anyone else? Okay, thanks guys.